thank you for all coming today. It's great to see such a turnout and such a participation online. So welcome to everyone again. People were wondering why we chose this theme of applied earth modeling. I just thought I'd speak to that a little bit. As we look deeper to find economic deposits in complex geology, the role of the geologist is becoming more and more challenging. We need additional insight to ensure exploration success. Companies have been making advancements in their exploration project through the use of earth modeling, and the TGDG committee felt that this was a topic worth sharing. We have a very exciting lineup of speakers today, all of whom share a passion on this topic. And it's our belief, our humble belief from the TGDG, that your exploration projects will profit from applying the inspired ideas you learn here today. Our opening speaker is Ian McLeod. Ian received a BSc in geology from Queen's University in Kingston in 1978, which was followed by 10 years working as a geophysicist with Patterson, Grant, and Watson. While at PGW, Ian worked on both regional and prospect scale geologic interpretation and geophysical data collection in North and South America, Australia, Indonesia, and Kenya, and a good amount of teaching of advanced methods of interpretation. Ian co-founded the software company Geosoft in 1982 and Geosoft Incorporated in 1986, where he continues to work today as chief technologist, and I have the pleasure of working with him daily. During the 1980s, Ian led Geosoft's pioneering work to apply computers to exploration, always with a view to improving the efficiency and effectiveness of explorers. Ian has authored and co-authored many commercial exploration applications that have helped transform large volume spatial data processing for practical use. Ian has also written numerous technical papers on new data processing and modeling algorithms that are widely used today. Ian was chairman of the Technical Program Committee for Exploration 97. Ian will set the stage for today's theme on applied earth modeling. Please welcome Ian McLeod.
Thanks, Lorraine. I want to acknowledge the Geological Discussion Group in particular. I wasn't aware you were around for 60 years. There's another group in Toronto called the Canadian Exploration Geophysical Society, which meets and has similar sort of format and forum and mainly deals with geophysical things. But one of the themes that I hope you're going to see today, and you certainly will see it with my stuff, is how important it is to integrate and collaborate as explorers, geologists collaborating with geophysicists. And when I've come to the Geological Discussion Group meetings, I've seen more and more geophysicists show up there. I haven't seen any geologists show up at the KEGS meetings yet. But going forward with what we're doing, a key part of that is about collaboration and being able to talk among geologists and geophysicists together, and geochemists for that matter, if you like to wear a geochemical hat. But hopefully you're going to see that as we go through the day. So thank you to the Geological Discussion Group for putting together a forum like this. Especially thanks for pulling on geologists and geophysicists around the world through the web as well. I think that's all great. The outline of what I'm going to be talking about today, I've just broken it into 4 bits. I'm going to say a little bit about exploration risk in 2014, being the year we're coming into. I'm going to talk about what is 3D exploration. It was used in the title to attract people to this talk. And then I'm going to talk about 3D geologic modeling of geophysical data specifically. And my intention in that discussion is to start to get geologists to understand what we're actually doing when we're modeling geophysical data to be integrated with geological modeling. So that's going to be very much from a geologist perspective as opposed to a geophysicist perspective. And finally, I'm going to just walk through a number of examples, each of which teaches us something a little bit different on how to think about geological modeling and the role that geophysics has to play in that modeling. So let's talk about exploration risk in 2014. Now, just before jumping into that, we all know that we're experiencing an exploration downturn right now. Exploration it's tough. Our business goes through these cycles. This is the 4th one I've been through, so I've experienced them before. They always look a little bit rough right now. The good news, it can only get better, we hope. But these things, they cause us to really focus a lot more on what's important as we're doing exploration, because money is thin, and one of the things that we have to watch out for is making sure we're making the next decisions correctly to minimize the risk of whatever projects we do have going on. This is really all driven by a serious cost pressure that we're basically living under. So exploration risk is acutely sensitive right now. Now, last week at the Quebec Mineral Exploration Conference, a gentleman named Richard Shoddy from UWA in Australia presented a keynote talk that showed the trends in exploration since 1960. And he particularly focused on trends over the last 10 years. So we could kind of we could see the forest for the trees and get a sense of what it is that we're going. Now that talk had over 50 data graphs in it. So for those of you who are statistically inclined, I really recommend that talk. You can find it online, and there's a lot of stuff to think about if you like statistics. But I'm going to pull 3 of his slides because they're relevant to what we're talking about today. The first is this one, and this graphs the number of meters drilled each year since about 1972 relative to the amount of money we've been spending on exploration. An overlay of this is that the cost of per meter drilled this year is twice the cost per meter drilled in real dollars of 2000. So now it costs us about $210 per meter, and this is in Canada and Australia, which is the subject area that he studied. $210 per meter to drill a hole. The net result of that is that proportionally we're spending about the same amount relative to the total exploration spend, but we're drilling a lot less. In fact, we're drilling proportionally half the amount of meters relative to what we're spending that we did in 2000. There's a pressure on drilling because of cost. Now next, and this is something we all know, by the way, some of these things are motherhood statements, is we're looking deeper. We're looking undercover, and we're looking deeper. We found most of the things that can be found easily. Yes, we still find a few things that aren't easy, but most exploration now is done undercover and deeper. And this graph clearly shows that. Really, at the early part of the century, everything, you had to see it stick out of the ground to find it. And now I really don't know what these super deep things are, but especially in the last 10 years, you can see even down here, the overall trend is down now to looking for things and finding things in the 100, 200, 300 meter part of the ground. Now, what does going deeper mean? It means 2 things. It means you got to drill more. We got a problem. Drilling is more expensive. So now that we're going deeper, we have to. It gets a lot hard. It's a lot more expensive to actually drill, put things in, holes into those things we're looking for. The other thing it means is that things are fuzzier. Because they're deeper, they're further away. They're harder for us to see. They're harder for us to characterize. So it makes the problem of actually sighting those drill holes even harder. Of course, it's undercover. We can't actually see it. So we are resorting more and more to other methods like geophysics to try and find those things. Which brings us to the third slide I pulled from his set. And this slide is showing what was the primary technique used for companies to choose where they wanted to explore. And the thing I'd like you to notice is the red thing at the bottom here. This is geophysics. Obviously, as we go undercover, geophysics is increasingly important as the main targeting tool for us to decide where it is we're going to look for deposit. Now, I think this is also unfair because a lot of this large part up here is about extrapolated from known mineralization. Well, a lot of extrapolation from known mineralization is done on the basis of airborne magnetics. That's the primary tool for regional mapping of geology to extend known geology into other areas. So I would suspect a lot of geophysics is involved there as well. So that's the other thing is geophysics is very important today and going forward. So the conclusions from all this is exploration risk is reduced by drilling the next hole in the best possible place. The next hole could be the first hole on a project, could be the 20th hole on the project, or it could be the next set of holes when you're drilling off your resource. It's critically important that we make the best decisions to do that. Secondly, we have to do a better job integrating geophysics into the geological modeling problem. Geophysics isn't just fly a survey, pick some anomalies, do some modeling that the geophysicist does for you, and then take the result and start to work with that. Where we're going is we have to integrate thoughtfully what we're doing with geophysics together with what we're doing with geology to make the best possible drilling decisions. Well, let me now turn to 3D exploration, which I thought was an odd thing to throw out there. I think it's kind of neat that, hey, 3D exploration sounds like the new thing. But I'd like to challenge that a little bit. Let's first start with phases of exploration. Just to frame us all on all the talks you're going to hear today are occurring at different phases of the exploration process. Of course, things begin with project generation. Now, at project generation level, we have a conceptual model of what it is that we're looking for. With that conceptual model, we'll choose prospective areas. There may be regional areas that fit that sort of model. We're going to be collecting regional data, looking at government data, a variety of things to pull the kinds of projects we want to pull off. That leads to initial exploration, where we find more data on particular things that we want to work on. We will then start to plan geology programs. We'll plan geophysical surveys. We'll plan geochemical surveys. And that's where we're actually setting up gathering of data to start to look at particular projects. Once some of those surveys are in place, we get into prospect targeting. And that's where we're picking anomalies. We're picking particular things that we're interested in. We're doing interpretations now of what we think is going on in the ground, and we're targeting places to drill. And so this leads us to what I call discovery drilling, which is where we drill a hole based on what we thought in our head was the model. We either hit something, we learn something no matter what, we decide what to do next, which could be more surveying, which could lead to drilling, etc. So there's a process of improving and improving what we think of as going on in the ground as we go through this discovery drilling. Now, if we're fortunate enough, and we all know the odds are very low of finding something at this stage, but if we're fortunate enough to find something, then we get into what I call resource definition. And now we're starting to drill the thing off and figure out how big it is, its extent, etc. That's something that we're all quite used to. And once we get to mining, you've got the infrastructure in place, and you'd like to find more ore beyond the first thing we found, and that's when we get into resource expansion, which we typically call brownfield, and we start to look for things nearby the mine that can reuse the resources we have in place at the mine. A few things to note here. One thing is that we tend to be mostly two-dimensional at the project generation initial exploration stage. And as we go deeper and deeper into this exploration phase of exploration, we will move more and more to the 3D world quite naturally. When we're actually mining, we almost always have 3D models, especially in computers, and that's been around for a very long time. But the power of computers now is starting to push these sorts of thinking back upstream so that we can use them earlier in the process. It used to be these very powerful systems were really only able to be handled at this sort of cost level. Now we can do quite a bit more powerful things further up this way. So there's 2D tends to be this way, and 3D tends to push down this way. A couple of other things is, one is that we get a lot more data rich the further down here we go. So as we get more and more three-dimensionally data rich, the demands on computing and the way of thinking about the program or the exploration program start to increase with that richness of data. So that's another aspect that's brought us to today, where we're looking at more intense projects. You're going to see a lot of data richness today, especially at this end of the profile. The other thing that changes as you go this way is we go from a conceptual model earlier on to, when we start to do the discovery drilling and resource definition, we start to get very specific. We go from an idea of mafic volcanics and a pluton to a specific granodiorite with a particular fault and a particular mineralogy. Now that specificity means that we can get a lot more detail here, but the crossover doesn't happen until you get down into here. At this stage in the process, there's still a lot of unknowns. We can argue over whether it's a mafic volcanic or something else. And so there's a lot more flexibility at this stage in the processing. Now, my own experience, and especially the things that we do at Geosoft, are more working in the earlier stage. So what I'm going to be doing in the rest of this talk is focusing more on this stage of the exploration process. And I'm hoping this is going to lead the thinking, that we're thinking correctly as we hear some of the other talks and they start to move later in the process. Okay, let's go back to, you mentioned I graduated in the late 70s. I'm going to go back about 30 years to 1980-ish, working at Patterson, Grant, and Watson. And I remember this. I walked into the office one day, and Norm Patterson slapped a map like this on the table and said, "Ian, tell me what's causing this." Okay. Now, I know there's some geophysicists there, and I know there's some geologists that understand geophysics. This is a contour map. It's a contour map of the total magnetic intensity. And any of you who have interpreted data, I know, will have immediately seen a 3D model in your head. Our brains will have converted this to 3 dimensions, and we'll have thought of what is the thing causing this circle here and then this anomaly in the center. And in our heads, we will start to build a 3D model of what that thing looks like. So 30 years ago, the 3D processor we had was our brain. And I suggest today the most powerful 3D processor you have is still your brain. And so my opening question was, well, what's new about 3D exploration? We've always done 3D exploration. The only thing that's changed is the tools that we use to do that 3D exploration have got more sophisticated, and we're doing more and more of it with the computer to help our three-dimensional brain. Of course, geology has always been 3D, so therefore exploration is 3D. It always has been. Now, the first thing I would have done 30 years ago is I would have pulled out the color box of pencils and I would have colored this. Of course, today you push a button on a computer and it colors it for you. Now, there's a really important point here. Some people see this and go, great, the computer colored this for me. Wasn't that great? I just saved 2 hours. But actually, the way to think about this is what the computer did was it gave you 2 hours. So you could go and do some research on the geology. So you could go and read more papers on what was going on. So you can go and think about more information to bring to the problem. The computer saves us time by doing things like this for us easily. It doesn't give us answers. It gives us time back. And I really encourage people to think that way about how they use computers as a way to give them time to be much more thoughtful about their exploration process, as opposed to a computer is not about pushing a button and giving you an answer. Okay, once I've done this, I had understood that, well, now I've got this, I can see much better a magnetic high, and I'm imagining there's some magnetic feature that's making this circle. And in those days, I would have drawn a profile across here, and I would have done some modeling. So there's the thing I'm modeling. By show of hands, who has run a MacLeod model in this? Oh, good, we got a few. 6 people. Now, this was modeling circa 1982-ish, 83-ish. And what we have here is we've taken a profile. This is that profile. And what we've given this program is a whole bunch of assumptions. We said, assuming you're a body that looks something like this, assuming you have a half strike length of about like this, assuming you're magnetized by induction, assuming, in fact, there's a whole bunch of assumptions built into this. Given all these assumptions, the program will give me the best fit that will explain that data. It's really important to understand that we're saying, assuming all of this, this is a reasonable model. We are not saying that this caused that. We are just saying that this is a plausible reason for this if you can accept all of these assumptions. And the fact that this thing gives me exactly what I've observed, well, that's evidence that I haven't made a really gross mistake. But that's about it. I've fit the data, and I've got one possibility here. Now, I'm going to come back to that theme a bit later in the talk. If I was asked to do the same thing today, in fact, I was. This particular anomaly was given to me last year by Peter Cashin at Quest Minerals, and he did the same thing Norm Patterson did to me 30 years ago. He said, here, what caused this? Well, today I'll feed that into an inversion program like Voxy, and I'll ask it to solve that problem for me in 3 dimensions. It's doing the same thing MacLeod did 30 years ago, but now it's doing it in 3 dimensions with different algorithms and a different set of assumptions. And what it does is it produces for me what looks like magnetic magnetization in the ground, characterized by these pink things. And you can see my initial profile here. And if I tilt this thing up, I can look at it on its side. Now, a lot of people look at this and say, well, that's a big advance because it looks more geological. In fact, I've been really surprised by the number of really good explorers that tell me they like this a lot better because it looks more geological. But in fact, this model isn't really better in terms of giving me information that fits the data. Both the models fit the data. This is just giving me a different view of the data in 3 dimensions and a different way of thinking about the data. Both of them were right. But because this one looks more geological, the geologist is more likely to accept it and work. But I think what they're really saying is the investor is more likely to drill into this thing than they are into that little stick diagram in the other one. So as geologists and explorers, we do have to separate the difference between how we're promoting the prospectivity of our project from the reality of the science. Scientifically, there wasn't a lot of benefit here in terms of just what you're looking at from a geological point of view. Having said that, One of the benefits was the simple fact that I tilted this up and looked at it this way. So one of the real benefits of modern 3D visualizations is simply allowing our brain to look at the problem in different ways, more richly, look for different relationships, and I know all the talks are going to get into these themes. I'm now able to think about that project differently than I could 30 years ago. So for example, you can see this little wiggle here. And then when I look at the contours, I see that all the contours are sharing the same little wiggle. And I would probably more confidently interpret a fault running down through here, for example. That's the thing that geologists and explorers will do. And maybe that fault is going to be important later on in the process. So the 3D has helped me in certain ways. But fundamentally, in terms of the physical problem, it's similar to what we've done before. And there's the, sorry, I should have shown that earlier. There's the MacLeod, for example. This is what we were seeing along this little profile. So 1980, 2013. So Earth modeling for exploration, it's a methodical process of building a geologic model of the Earth's subsurface that best explains the observations we have. That's what Earth modeling is, and that's what our job is as explorers. Geophysics provides information about physical properties and geometry of the Earth. Geological mapping provides information about lithologies and structures. Drilling provides point measurements in 3D, of course, of rock type, property, and structure. Geochemistry provides measurements of mineral and element concentrations. And many other data sources, remote sensing, thematic mapping, you name it, other sorts of data that can be brought into my problem or other things that are all inputs into our geologic problem. And the true geologic model is the one that explains all of the data and observation. A little anecdote from this is I taught geophysics in Brazil in the 80s, and there was a huge rift between geophysicists and geologists. The geologists just didn't believe geophysics at all, and the geophysicists just thought the geologists were simple-minded people. It was just the classic thing. And we had a 20,000 nanotesla mag anomaly across this property. I mean, they have whopping big anomalies down there. And so there's something magnetic there because we measured 20,000 nanoteslas above background. The geologist said, I have mapped every inch of that. It's all granite. The geophysics is wrong. And then we said, no, that 50,000 nanotesla anomaly is not wrong. It's real. It's 50,000 nanotesla. If the geology doesn't explain that, the geology is wrong. And that caused a big problem. But the true model explains everything. And so it isn't one's right and one's wrong. It's the process of thinking it all through so we get the model that explains everything we have. Another way of thinking of this graphically is there's a wide range of geophysical fiction, a wide range of geological fiction, and there's a wide range of geochemical fiction. And it's the intersection of all of those that is the truth. And that's what we're seeking with 3D modeling. I noticed that as well. This was made by Rob Ellis. He is a geophysicist. So anyway, you should be proud of that. 3D geologic modeling of geophysical data. So let's dig into geophysical data. Again, because it's so important undercover and so important in going deep, it's important for us as geologists to understand exactly what we're doing with that stuff. First and foremost, geophysics does not measure geology. Geophysics measures or is sensitive to rock properties. And in fact, many geophysical methods aren't sensitive to the actual property. They're sensitive to the difference in property from one rock to another. Most methods are sensitive to the contrast from one rock to another, especially gravity and magnetics. And it's really important to remember that. If you don't have a contrast, you don't see things. It's the same thing with seismics. Seismics needs density contrast to see things. Anyway, this is your standard Geophysics 101. Shows the actual rock property that we're measuring for the different geophysical methods. And I've thrown up some examples here of the kinds of things you see in nature that will explain differences in rock properties. I'm not going to belabor this too much. But remember, geophysics is measuring properties, not geology. So back to this little model that we looked at. Let's think about what we've actually done here when we've created this 3D model. I'm going to tilt this up, which is the lovely thing in 3D. I can sort of have a look at it from a different spectrum. Now, somebody has given, in fact it was me in this case, gave this to Peter Cashin and said, here's what I think is going on in the ground. But how did I actually come up with it? Well, first of all, what I actually modeled, I modeled by dividing the Earth up into a whole bunch of little cells. And then I asked the modeling program to tell me what is the distribution of magnetization in all these cells that explains that data. And so actually what the program gave me was this voxel. It's a three-dimensional voxel, and I've taken a slice across it. This is actually what the program gave me. And then what I've done is within that model, I had some reason for choosing this particular isosurface and deciding, well, that particular magnetization value I think is geologically reasonable. If I peel that back, that isosurface back, you'll see that this is actually what was there. And why did I choose that one? Why didn't I choose this surface? Or why didn't I choose the small one? Actually, I don't have any reason for that. I just chose it because I thought Peter would like the other one better. It's true. And there's nothing wrong with that, but I need to, when I'm having a discussion with a geologist about that, I need to explain that. And you need to ask your geophysicist about, why did I get this isosurface? What was the reason for that? What does it actually mean geologically? This is the real model, but these aren't particularly appealing to geologists typically because they're too mushy and soft. But this is a reasonable model for what was going on in the. Of course, if I throw on that model that I would have calculated 30 years ago, it looks like this. Now, it's nice that these things are somewhat reasonable. They have reasonable sort of depth, but they are very different. This is showing two things, which actually quite interested Peter, because now he's got two things to go looking for with something in the middle, and so it's possible there could be two edges. This one has the stick figure. It ran it off to depth, so I wasn't saying anything about depth. But both of these explain that data. So now I'm going to talk about the most important thing I think geologists have to understand about geophysics is that geophysical modeling is non-unique. And what we're showing here are 6 versions of a density distribution that all produce exactly the same gravity tensor model. From the gravity tensor data alone, you cannot tell the difference between any of these models. What makes the difference are the assumptions that are made on behalf of the interpreter. So in gravity, for example, we're sensitive to density contrast, and the biggest density contrast, of course, is between the air and the ground. And so one of the big things you've really got to be careful with gravity data is correcting for that ground air, modeling that ground air interface to remove that from the problem, because it's the biggest problem. And everyone who's doing this right now has got pretty good algorithms for pulling that off. It's also the closest to where you're measuring, so it has the biggest impact. The next biggest density contrast is between your overburden and your rock. And that's also closer to my survey. And so you've really got to think about how to deal with that. So for example, if I knew that all my rock was the same density, and I said, well, just tell me how deep the overburden is, I could get a model that shows me this. And it's simply the overburden depth. And with that assumption, this is a correct model, provided everything is the same down here. This could be a perfectly valid model. If, on the other hand, I said, no, I'd really like things to be really small and compact because I've got a good reason for thinking it's all compact, I've removed the topography, I've removed the overburden thickness, then this is a reasonable model. Or maybe this one where I allow it to be a bit fuzzier. Or if I've done some mapping and everything is lying vertically, then I could say, well, emphasize things to be lined up vertically, and this is a model. I cannot tell you which of these is right, and I'm not going to, because they're all right. The difference in what's right and wrong is the discussion you have with the geologists about the assumptions, and what is the reasonable set of assumptions on how to pick the right thing out of here that's going to help me in my experience. All right, now let me go into some examples that demonstrate these concepts. The first one is just kind of a reminder of something that we often see overlooked, which is making sure that if you're going to do a geophysical survey, make sure that that geophysical survey is going to measure what you're looking for before you do the survey. And in terms of reducing exploration risk and making the most of your money, you should be making sure that you're not wasting an exploration project or a geophysical project, or worse, wasting the season it takes to go and pull that off. Because if you go and fly something or do measurement, you've lost the time as well as the money to find it gets nothing. So just a quick set of slides from Bathurst. This is the Bathurst number 12. It's a well-known VMS deposit in New Brunswick. It was found with EM along a profile like this. This is the massive sulfide right through here. This is probably the lowest cost airborne EM surveys you can do would be frequency domain DIGCHEM surveys. And this is classic bump finding. This is the deposit right here, which you can see right here on the conductivity map. And the question, if you're going to be exploring over here to the east, the question is, can DIGCHEM find prospects over here? You can actually see that that there's a a conductive a sedimentary layer that we're getting over here, and we want to know if we can see that. Problem looks like this. This is the slightly conductive carboniferous rocks here. Can we find conductors like that? Simple model. And we'll run through what it looks like at surface. There it is with no overburden. A little bit of conductive overburden, 10 meters. Here it is with 20 meters, and here it is with 50 meters. The noise level for a DigChem system is about 10 ppm, and you can see we cannot see things at 50 meters, and we can just barely see them at 20 meters. So now you've done something simple to determine what kind of survey to use. If you want to look deeper than 20 meters, you really should use a more high-power system. And by the way, this sort of modeling can be done for you by any geophysical contractor that would be doing the work for you. The place to get this done is ask people to do it for you to make sure that they can find what they're looking for. Now, this is particularly true for things like EM surveys and gravity surveys, I would suggest. Other kinds of surveys, there's a lot of other kinds of ancillary data you're going to get from them. Mag surveys, for example, it's almost universal. You almost always do mag surveys if you can't get them from the government. But you need to be thoughtful right at the beginning, and this is where the modeling starts. What am I going to expect to see when I go out and do some work? All right, let's dig into perhaps one of the simplest sorts of conceptual models. And this would be the kimberlite model. This is an anomaly, a magnetic anomaly from Diavik. It was actually discovered by an airborne survey. It's near the Diavik mine, and so they're just looking for more kimberlites that have diamonds in them. So the terrain is prospective. There are geochemical indicator minerals, specifically around this one that focus interest on this one. And this group did a ground magnetic survey to really isolate where that thing is so they could drill it. Okay? Next step. Well, the next step is to actually feed that magnetic data into a modeling program and produce a geophysical model to give us an idea of what is the magnetization distribution in the ground that would explain the location of that, or tell us where to drill, basically. Now, in this case, you could see it was a negative magnetic anomaly. The assumption is that it came up when the Earth's pole was reversed, which is why it's negative. And when you do the modeling, you get a negative susceptibility model of the pipe. Well, that looks pretty good. Let's go ahead and drill it. So in this case, they drilled right into the gut of it. They drilled one vertical hole just down the top just to make sure that there was a kimberlite there and it wasn't just a lake sediment feature, and that, yes, they found some kimberlite. And then they offset and they drilled these two holes. But the problem is both of those holes at the cost of, I think, $300,000 or $400,000 mobilization, they missed. They didn't hit anything. But clearly in the model, they hit the model. So the geology and the model don't agree. Afterwards, they came back and then they said, well, there's something wrong with the modeling. Now, this is where I sometimes hear from geologists, they say geophysics doesn't work. Geophysics does work. It's just, in this case, the set of assumptions we used in the modeling was incorrect. So they went back to this project and they said, well, one of the things that we know about kimberlites and surrounding rocks is that the boundary is very sharp and they tend to be very focused. So these smooth inversions that just kind of spread out the magnetization isn't a very good assumption. We like an assumption that makes that tighter. So we ran this again with focusing. And then when you focus it, now you get quite a bit tighter anomaly, and now you see that both of the holes are missing. Now, hopefully there's some skeptics out there asking, well, why did you pick this particular shell? Maybe you could have just pulled it back so you should explain the holes. Well, this particular shell in this case was chosen because that's where we had the maximum gradient on the magnetization changing. So that's where we're assuming that's closest to the edge. If it is truly a sharp contrast in there, that's going to be close to the edge. And this explains these two holes being missed. So if we thought of doing that earlier on, we would have changed the location of the holes. Interesting, this hole here would have intersected this, but just because of the local rock conditions, the thing veered off to the right and missed it by a little bit. They haven't gone back to prove this up. That would be next season if they do. but the cost of mobilizing a drill rig up there is about $250,000. It's a pretty small kimberlite. They may never go back and see this. All right, let's jump to Brazil. This is for you, Alan. This is the quadrilateral ferrífero in the Minas Gerais, Brazil. I think Belo Horizonte is up here somewhere. Anyway, this is probably the most prolific iron ore deposit in the world. In fact, all these little yellow things you see all around here are iron mines. And if you've ever been there and driven up this road, you just see the iron mines from the highway. It's a pretty impressive piece of geology. These are the actual magnetic unit, or the unit being mined is called the newtaberite, and it's a quartz iron formation. And I've just drawn the trace of that, where that's been mapped on here. Now this is in Brazil. The Earth's magnetic field is close to horizontal, and the magnetic method is particularly thorny because of this. We're lucky in Canada because the magnetic field points pretty close to straight down. But as you get to middle latitudes and low latitudes, you run into this problem. Now this is great magnetically for this part because the magnetic field intersects this sideways. And by the way, this is a very steeply dipping feature. We know because it's very well. And so we're seeing this nice big negative that we're used to seeing in low latitudes. And then when the thing turns north-south, we gets a little bit more problematic. You can still see something there, but it gets quite messy. Now on the right, I am showing the result of a 3D model response. So we measured this. If we model the whole thing in 3 dimensions, I can produce this response. And I'm going to show you a few results. Every single result will give me exactly this same response. There's no difference in what I actually get from the model, but the models are very different. Taking that northern profile from north to south, you can see the teberite right up through here. And in this case, this is the normal conventional susceptibility assumption where we assume it's magnetized in the direction of the Earth's field. And we can see that this is really quite bad. It's showing us a positive magnetic feature here and a negative feature here, and the teberite runs right up the center. If I model this by removing that assumption, saying allow the magnetic field to rotate into whatever is going to make the data fit the best, you get this result on the right. And so now we've had really a dialogue between a geological map and the people doing the inversion to think about this, remove an assumption that's causing a problem, and sure enough, now this lines up exactly with the iron formation, the map to teberite. In fact, you can see the mines right on the top of this thing. And also, all the local geology here shows steeply dipping to the north. Now going to the southern one, across this profile, same idea. We model that. The red and the blue are what were modeled if you assume just induced magnetization. Allow that vector to vary, which you can see in here, and now it will line that up right underneath the teberite. So in low latitudes, this particular assumption we found is really important to think about. Do you have remnants? Do you have a reason for that magnetization vector to vary? Allow it to vary, and then you're going to get a better result. And it's dramatically better. You would have made big mistakes trying to use modeling based on the original conventional susceptibility. My own recommendation is if you're ever in low latitudes, this is the only way to model magnetic data, is with a varying magnetic direction. Now the same is true in mid-latitudes. This is the Osborne, Australia project. We actually did this 3 years ago with Barry DeVette, who was the person who motivated us to develop this technique. And this shows susceptibility modeling of the Osborne deposit, which runs this way. When we allow the vector to change all by itself, it will naturally follow that. Now this was a few years ago before we had focusing, et cetera, but this was a dramatic improvement in bringing that magnetic information into the geologic model. Quick one on the Sudbury Basin. Now on this one, we're looking at the Podolski Mine owned by FMX, which is in the top northeast corner of the basin. And the easiest way to find a mine, as they say, is look for the head frame. So we found it. There it is. This is one of the more modern kinds of deposits we're finding in the Sudbury Basin, which are quite deep. Well, it's about 2,000 feet in depth down here. They had been mining the Whistle Pit for some time, and so this is a recent deposit. They flew a survey to see if they can actually pick this up in the geophysics and obviously find more of them or help them distinguish more. So we've got mag, gravity, and terrain. You can actually see the whistle pit right here. And because this is a well-known mining district and a mine, we're now getting into the space where we actually are very data rich. So this is a GoCAD model of what they really know a lot about this area. And so now you're bringing a lot more information to the problem. All the units are very well mapped and very well defined, and the deposits are marked in here in different colors. Now when we took that gravity data and we modeled it the first time, it put a gravity high right here, whereas we know that that deposit outline is right here. Well, that's interesting. We're picking up a gravity high. It's quite dislocated. If you're drilling 2,000 feet to try to hit this thing, you sure wish you'd be over here and not over here. If, however, we model the magnetics first, and then we feed the magnetics into the gravity model and ask the gravity to prefer the magnetic model as it's fitting it, it actually ends up putting it right on the right spot. So what have we learned here through thinking and through looking at the models? We've learned that, well, in this case, in this area, if we're going to do more of this, we should model magnetics, feed the magnetics into the gravity, then take the combined result, and that's going to give us a better chance of spotting that hole in the right place the first time. Now, the last example I'm going to show is one from Abingdon Resources in the Yukon. This is an intrusion-related gold deposit. And they have this, here's the Yukon border here. You can see where the deposit is. They've got this little piece of land here that they've claimed. They also have an area up here where they've done some pretty good mapping and they found really good gold showings, and they've drilled about 10 holes into this one. So it's a classic case where they've got some good intersections in this area, and then they want to know what else is, what is the best way that I can tackle looking through the rest of the area. As an intrusion-related deposit, these things look quite interesting because they look like it's a granodiorite type intrusion, and so you got an idea of some things going on down here. So in directing the rest of the program, how do I do this? Well, I'm really glad to say sections are not dead when you've only got 10 holes. What the guys at Terra Logic did is they just made up some sections of the 10 holes, and then the geologists got to work and they just drew the simple geology, as simple as they could figure out from those holes. There's a skarn, there's a Hornfelt contact metamorphism with the granodiorite, and then here's quite a big Hornfelt down here. Then they took these sections and they draped them in 3D. So let me start to have a look at this in 3D so I have a sense of what's going on. And then they just connected the skarns together, the Hornfelts together. They would produce a simple wireframe of what they think is the skarn and what they think is the Hornfelts based on very little information. So now at least I've got some kind of geologic model to start to go from. And then they modeled the magnetic susceptibility. And the magnetic susceptibility, when just left on its own, produces a big blob like that. Okay. In discussions with the geologists and the geophysicists, and looking at the core logs, they know that the Hornfelt is magnetic, the skarn not so much. And so they really feel that this is an indicator. We can use the magnetic modeling to help find these Hornfelts, which are an indicator of prospectivity in this case. So now the thing to take away from here is I'm now going to start to iterate. So I'm asking what ifs. Because the computer could make that model so quickly for me, I could say, well, what if I do this? And in this case, what they did is they said, well, let's try to constrain the model to line up with the Hornfelt only. And the way we do that is we say, well, start off inside the Hornfelt and see if you can stay there. And as the program's working its way through, it turned out it couldn't. It squeezed out of the thing and said, I can't fit this with this, and I'm having to squeak out. And not only that, I'm getting artifacts of things off to the side that don't make sense. Okay, this isn't working. This isn't making sense. Let's try something else. Let's just focus. We know it's a very focused focus unit. Focus it, please. And the good and the bad news here. The good news is it actually looks very similar to what we did when we tried to constrain it. So that tells us there wasn't any benefit to constraining by shape. But it is giving us a slightly better sort of dip shape with this. So we can rule this one out, and if we have to use something like this, that one's a bit better. So another step, and let's focus on the edges to limit the susceptibility. Now in this case, and limit the susceptibility. In this case, we said we won't allow the susceptibility to be higher than 0.002 or something that we measured from rock properties. And now we've got a much better agreement with what we think we're doing. And what we've done here is we've basically tuned the method. So now we've got an approach to modeling the geophysics that's going to give us the best chance of finding what we need to find in the rest of the property. Remember, every single one of these produced exactly the same magnetic field. So it wasn't that one of these is right magnetically, but one of them gives us a better shot at being right for this particular geologic model. So back to what we know, we have this area, we have a 3D mesh underneath. This was the original project. We have an airborne magnetic survey over the whole project. Let's take that model, that approach, and apply it to the whole thing. And what we find, this is the original one that we just modeled. There's that fit that I just showed you. And then here's the mapping of the other Hornfelts. And if I look at this from the bottom, this is quite a plausible thing. You can imagine a granodiorite up in the middle pushing up, causing these contact Hornfelts. And now we've got targets for the next season. Now they just need an investor to help them pay for the holes. Anyway, let's just talk about learning. We'll close with learnings on this. So first off, the Earth is 3D. Exploration is a 3D problem. Undercover and deep exploration demand a better understanding of 3D geology of our prospects. And that's more and more important as we're going forward. Deeper, more expensive drilling. Geophysical modeling in 3D is an integral part of building models. So it's a part of the building models. It's not something the geophysicist just does and hands you a model. It's something you've got to work on together. Geophysical models are not unique. They need to be thoughtfully integrated with the other information to find the best geologic model. And computing gives us time to explore, to think, to collaborate, and build the best possible models of our Earth. So think of how that iteration, the computer, the ability to go through things fast is what gave us the time to collaborate, think, and really work on it, because it's us and our brains that are going to really develop these things, and the computer is a tool. So thank you. There's many people to acknowledge for this, so here they are in order of appearance, and thank you very much.